Let's add a few more points to whether space-based solar power can work as a source of clean energy for Earth. This is a nice news explainer from Nature, which is by Elizabeth Gibney, appeared in Nature on 1st February 2023. As a prototype prepares for tests in orbit, Nature looks at 5 biggest challenges for space-based solar power. We have said some of these things already in the previous podcast, so we'll repeat them, but that's okay. This is an image or a schematic or an artist's rendition of the European Space Agency, which is investigating whether orbiting solar arrays could beam renewable energy to Earth, as shown in this artist's illustration. So this highlights many of the problems. How would you deploy a scaled solar panel array in space? Would you send them to space piece by piece and then robots will assemble them, or will it be some kind of a system that's folded up and then just can be unfurled in space? How large does it have to be to supply energy at a utility scale level, order gigawatts, for example? And how to actually transmit the energy is something we already discussed, but we can discuss it again here in the 5 things we have to worry about. Just to remind ourselves, the European Space Agency's Advanced Concepts team put this out. So incident solar radiation in orbit, the intensity of sunlight is much higher than the intensity at Earth's surface. Plus, on Earth you have day and night, so nighttime there is no solar, but you can stay in space and you can get sunlight all day. Secondly, sunlight capture energy regulation. Sunlight is converted into a current, then prepared for radio frequency beaming to Earth, the Moon, or another planetary surface. So how to transmit the energy is a key factor. Typically, to go through the clouds, you need to be in microwave, and microwaves tend to spread out as they propagate, so you have to find a way to keep them together, etc. Beam capture and energy conversion. The energy beam is captured with photovoltaic cells or with an antenna that converts electromagnetic energy into electricity. Satellites can beam energy down to a single ground site or to several locations around a planetary object. The scales of these utility or receiving stations also have to be large to capture the energy coming in terms of microwaves or radio waves. Okay. 5th one here, did we skip? So after second I skipped third, sorry. Power beaming. Energy is sent down to Earth using phased arrays, laser emitters, or other wireless technologies. The energy beam must be accurate, reliable, and should retain as much of its power as possible as it travels through the Earth's atmosphere. The arguments have already been made that even if the efficiency of this transmission is only 10 to 15%, we can still work at a very economic scale compared to nuclear, for example. The 5th one, power transmission. Systems that collect the space-based solar power on Earth must be safely and sustainably integrated into existing power grids. This is true for all renewables right now. Power distribution is also vital in science, exploration, and colonization missions. So people are already talking about putting up nuclear power plants on the moon, for example. Finally, energy utilization, as well as having the potential to aid Europe's goal of becoming carbon neutral by 2050, space-based solar power technologies could provide the flexibility and reliability required for science and exploration missions where other power sources are limited. For example, rover missions during lunar night. Okay, so you can imagine that you are somewhere and you need power at night, and then you can use these beaming solar space-based panels to do that. Caltech researchers have built a prototype space-based solar power system that launched in January and is now preparing for tests in orbit. So already prototypes have launched, and Caltech has found a way to build foldable solar panels so that you can roll it up, send it, and just unfurl it instead of having multiple panels being put into space and then robots trying to assemble them in space. As an example, the required size of the solar array in space would be about 100 times as large as the space station that's floating around, the International Space Station that's now roaming around for orbiting around the Earth for couple of decades. So looking at the various issues, what kind of solar cells would be used? The solar cells need to be lightweight and efficient to keep launch costs down. This is true for anything you launch into space, whether it's a spectrometer or a sea level measuring mission, CO2 measurement, whatever else. Each kilogram of panel should produce 1 to 2 kilowatts of power, says David Humphrey, a physicist who leads technical work at the United Kingdom's public-private space energy initiative. That power-to-weight ratio is around 50 times greater than for conventional silicon cells on Earth. Most designs aim to boost the solar cell's exposure to sunlight using concentrators, mirrors, and other innovative structures. So the elements that these panels are exposed to in space, temperature, and various other energy from the sun, they have to deal with. They have to worry about how to protect these and make them operate for long enough time anyways. Will it all be worth the effort? Space agencies and nations think that space-based solar power might contribute to the goal of achieving net zero carbon emission by 2050, but we have to prove this is going to actually be net gain for the planet, says Jones. Space-based solar would certainly be much more expensive than terrestrial solar power. However, it could rival the cost of other sources of continuous low-carbon power such as nuclear or gas with carbon capture technology, says Carpenter, although more economical ways of storing renewable electricity on the ground could diminish the case for space array. So this is going to play out with costs, design difficulties, technologies, launching costs, life cycle analysis kind of approaches to compare to on the land, on Earth systems with storage. How will the solar power reach Earth? We already mentioned this a little bit. This is arguably the biggest challenge. Although laser beams transfer energy efficiently, clouds can block them. To avoid this problem, researchers hope to convert the solar array's electricity into microwaves, which pass through the atmosphere without losing much energy. However, microwaves spread out as they travel, so engineers will need to carefully synchronize how the waves are emitted and use kilometers-wide receiving stations to collect them. Converting solar energy into electricity, then into microwaves, and back into electricity on the ground will inevitably incur some losses. Nobody is going to consider this idea seriously until those losses are significantly reduced. On the land, you have to increase the efficiency of solar panels, but if you put them in space and say we don't care about efficiency, there is enough power being generated, but then you have to worry about the efficiency of transmitting it to Earth and converting it back into electricity. ESA estimates that only 10 to 15% of the solar power falling on a space array needs to be delivered to the electricity grid for a system to be economically viable. Yet, achieving that would still require considerable advances in several energy conversion technologies, the agency says. Okay, so various people quoted here. How can a solar farm be built in space? To generate a gigawatt of power comparable to the output of power station on Earth, the orbiting arrays would need to be more than 1 square kilometer in size. That's more than 100 times the size of the International Space Station, which took a decade to build. An array would be assembled in space from modules that could be mass-produced and launched separately. Caltech's experiment will involve unfurling a tightly folded structure into a solar panel platform, roughly the size of a dining table. This is a demo only prototype, but the modules in a full-sized array could be up to 60 meters long. Finally, will it be safe? Space-based solar power. Beaming microwave energy from space is surprisingly safe. The beam's frequency will be chosen so that it does not disrupt aircraft communication. There are already satellites measuring sea level, for example, or rainfall, which use microwaves and lasers. And because of its power would be spread over such a wide area, the average energy density received by ground stations would be around 50 watts per square meter, says Carpenter, equivalent to the harmless level of microwaves that can leak from a microwave oven. It's within what would be considered a normal safety recommendation for human exposure to microwaves, he says, Carpenter. But researchers will need to prove that there are no adverse effects on humans, animals, or the wider environment. I think they need to take the lead from the mobile wireless industry that went through the same concerns, and to not trivialize these concerns but prove it with studies, says Jones. So we have to make sure that people are not scared and things don't get fried, because one misstep, one fried bird or tree or whatever, then all bets will be off in terms of public trust. So that's critical. But as the last caveat said, the communication people have already dealt with it and are using it widely, so this should be doable. Okay, let's leave it here for now.